So we're going to talk about I'm going to derive a little formula for kinetic energy when we're dealing with many particles or a collection of particles or rigid body. Okay, and we're going to start initially with just the definition of kinetic energy. So the kinetic energy, we're going to treat this. We're going to treat the object because it gets the point across without introducing introducing integrals and calculus. It gets the point across, right? So we can treat this body as if it's just a collection of individual particles rather than um, a continuous mass distribution, all right? And for our purposes, it'll serve our purposes because the difference is kind of not important for us, all right? So for each particle, um, the kinetic energy is given by one half times the mass of the particle. So mass sub I, because we're going to wind up summing up all of the particles. So we're going to sum over I. All right. So if we know the speed of the individual particles, the square of the speed times the mass of the particle, one half of that gives the kinetic energy of that individual particle. And written in vector notation, this is just the dot product of the individual velocities with itself. So this is just the definition of the dot product, really. Okay. Now it's going to be useful for us to treat that velocity in respect to a reference point. In this case, we're just going to label that point A. All right. So the speed of the ith particle is the speed of A plus the speed of I relative to A. Or no, I guess the velocity. The velocity of A, these are vector equations. So the velocity of particle I is equal to the velocity of the reference point plus the velocity of the particle I relative to that reference point. That's trivial, right? So then this Ti just becomes so we can expand out this dot product here. All right. Now, because this collection of particles is undergoing rigid body rotation, we have the situation where the relative velocity is the um, angular velocity crossed with the relative position. And that's due to the fact that these particles are moving in unison, as you know, as a rotation about omega. All right, and so therefore, we can sort of incorporate that into our definition here. So I'm going to leave one of these in the form of the relative velocity because it'll wind up being easier in the next few steps. But one of them I will expand into the omega cross with the relative position. All right. So now there is a vector. There's an operation called the triple product, and hopefully this should be hopefully I'm going to add this to the homework so that this won't be the first time you've seen it. But there's a whenever you have a vector A dotted with a cross product of B cross C, say, this is equal. We can permute the vectors in this operation. So this is going to be equal or, we can permute it one more time, so that would be what, like C dotted with A cross B. So you can kind of see there's a cycle, right? So A shifts around to the outside, C shifts one over, and B shifts one over. So there's a permutation between this thing. This is called the triple product. And this should not be the first time. I haven't made the homework yet or anything, but this isn't going to be the first time you've seen this. All right. So the one that we're going to want to do here, so in this case, we have a situation where A is the relative velocity, B is omega, and C is the relative position. And so this is the operation I want to perform. Okay, so I'm going to permute them to look like that. All right, on this last term. And so in that permutation, we wind up with, let's see here, so B shifts to the outside, so we have omega dotted with Okay, and so the reason we grouped it this way is because we're summing over the terms. We're going to wind up summing over all of the particles, and all the particles are associated with this I index. All right, so we can distribute this mass index into bring that into into these terms. All right, so like I'll show you what I mean. So whoops. Well, the 1/2 and the 2 are going to cancel. Okay. Now we can sum up over all the i's. So when we get if we want to know the total kinetic energy, we sum up over all of the particles. And so that's going to look something like this. So we're summing up over I, all of the particles. And so now we have to start recognizing, we're going to start recognizing some things. So first of all, the easy one, the sum of mi is just the total mass of the object. Okay. Now we got to think back a little bit, but there was a definition of the center of mass. So and the definition of the center of mass was of a collection of particles and as you can tell, that's precisely what we have here. Okay, so in this case, this will be the center of mass relative to point A would be given in that form. So what we have here is just mass times the center of mass. All right, and then this term here mass times velocity is just the linear momentum of particle I relative to A, and then R cross cross with the linear momentum is just the angular momentum of particle about point A of particle I. Okay? So the sum is just going to be the sum of the entire angular momentum of the entire object about point A. Okay? And so the kinetic energy is 1/2. We can substitute this in the total mass times the velocity of point A, or the speed of point A, I'm sorry, speed of point A squared, plus VA dotted with omega cross MRGA. Plus 1/2 omega dotted with HA. Okay? Great. So now we have a choice to make as to what, and there's really only two choices to make, two different cases for what we're going to choose. It's a choice as to what A is going to be. Okay? And so the easiest one may be if A is fixed. And if that's true, then VA drops out completely, and so the first two terms disappear. And what we have is okay, but recall that HA, the angular momentum, is equal to the inertial tensor times omega. And so in this case, and if you guys remember, if we express omega in terms of its magnitude and its axis, I think we covered this when we did the inertial tensor, but if omega is equal to the magnitude times its unit vector describing its axis, then T, or the kinetic energy, I can bring this omega out. So I get omega, magnitude, a number here and a number there. Both of those can come out to the front. So I get the omega squared. And then what's left is this. And remember, we called that, we gave that the name, it's the moment of inertia about the axis N. So that would be where this I is the scalar I. given by this quantity here that we discussed at the end of the conversation we had about the inertia tensor. And this is probably the form you're used to when it comes to, or this is the one you should remember from physics. And now the other case, A is the center of mass. Okay. In that case, the relative position of the center of mass with respect to A is, of course, 0, because the G and A are the same point. All right. So then we have the kinetic energy is 1/2 the velocity or the speed of the center of mass squared. And likewise, the center of, so the inertia tensor here is now evaluated at the center of mass. That's the only difference here. And likewise, we can do the same sort of thing and arrive at a term similar to that. Okay. And so this is the one you're probably familiar with from physics when we're talking about the center of mass. And then in a situation where it would be more advantageous for us to evaluate this quantity in terms of a fixed point. So if one of the points on the object is held down and has a velocity of 0, then sometimes it's easier to evaluate the kinetic energy, but in terms of that point. But remember that we're going to have to, a lot of times, the moments of inertia are given to you in reference to the center of mass. So we're going to have to use the parallel axis theorem to translate the moment of inertia to the stationary point. Okay, so we have to, that'll be clear when we start doing examples and whatnot.